Okay, so this is power management has been around for a while. We're aware of it. We understand how important it is. Over the last few years, power management has gotten to the point where it is potentially the most expensive aspect of running a cluster. You can buy your hardware, you can pay for your staffing, you can buy your software, you can get your facilities, but in many cases, power is going to be your single largest expense. Consequently, we're interested in optimizing the use of that power. See if we can, oh, whoops, I apologize. Okay. No, we're good. I just didn't realize we were, okay. Okay, so right now we're doing some very interesting projects in collaboration with NREL, the National Renewable Energy Lab, as well as with HP. HP has a large cluster out there. There's been a lot of advancements in the cluster if you look at them. Whoops, I apologize. Go back here. There's been a lot of advancements in the hardware that HP has delivered. These advancements come in two primary aspects. One is in terms of monitoring, to actually figure out the power utilization that's occurring. The other one is in the area of control, giving us very rich control over exactly how the power is used, not only across the entire cluster, but within individual servers. We do have a long history of collaboration with HP. We've worked with them on a lot of the most challenging problems that are out there in the high performance computing space, whether that be grid, whether that be cloud, dynamic provisioning. In this case, we're doing power with them, and it's been a really good project going forward. So the power problem, as you know, there's two big areas of power that are issues. One is the fact that sometimes you simply don't have enough power. It doesn't matter how much money you spend, there's not enough power coming to the facility. You are constrained by a cap. It's maybe 5 megawatts, maybe 10 megawatts, maybe it's 1 megawatt. It doesn't matter how important the jobs are, you simply can't pack more power into the facility because of the wiring, because of the infrastructure. The second one is the cost. The cost of power as a proportion of your total system continues to increase, and as we get down to exascale, we're going to see that even a bigger deal. We have to have 100x growth in power, and somehow we got to find a way to squeeze that into a power footprint that's only a small, a fractional amount larger than what we've got right now. So, as I was mentioning before, the power issue has gotten to the point that it now has the attention of most of the major hardware vendors. As you guys are shopping around, looking at your various clusters, you are going to find that power is touted very highly as one of the most important things about these new architectures. Particularly, the overall efficiencies are better, but as well as what we mentioned before, there's rich metrics, so you can actually determine exactly how much power not a given process is taking, but a given job is taking. And you also have power control facilities. You can actually change the clock rates. You can power down individual cores. You can adjust your BIOS. You can adjust your fan speed. You can do many, many things to control exactly how power is being consumed. So, state of the art. So right now, as we go to Europe, we go to Asia, and even in certain aspects of the US, there are some very strong rules that are enforced. A power company, a government, or other type of thing may enforce a rule that says this is your cap. Even though you're wired for more power, during these hours you cannot use more power than this. And there is a very large penalty associated with violating that. Well, to respond to that, some of the software vendors, I apologize, or hardware vendors, have enabled the capability where you can control the power that flows through a PDU. It may be rated for a certain thing, but via a software control, you can go in and say, I'm throttling you. I'm going to limit the amount of power that flows through. If you have these hard power caps, then it's a piece of cake to go ahead and enforce it. Now the problem is, your jobs aren't aware of this, your scheduler's not aware of this, so your scheduler and jobs are flowing through, trying to run as fast as they possibly can, and they're simply being denied at various times and told they can't. That is not the way to run a cluster. You don't want to have the system reactive to failures and shortcomings. A much smarter model would be to have the scheduler aware and the job was aware of this power and use it in the ideal manner. Route it to the right places, schedule the right jobs that fit inside of it, and use that thing ideally and proactively rather than reactively. Right here, independent decisions. That's the fundamental crux of the problem. You have one decision made on power capping, and then you have the scheduler completely independent, launching workload as fast as it can, many times in a bad way. Okay, so I think this is pretty obvious, but hardware power management is a great idea. It can only go so far in terms of solving the world's power consumption problems. A partnership between the hardware and the system management software is a great idea. The hardware can enforce certain things, it can report certain types of information, it can enable certain types of modifications to the environment, but it is really the scheduler that understands about the workload. It understands about the future, it understands about power profiles and other types of things which are absolutely critical. So NREL has a mandate to create a vision, not just a vision, but an implementation of radically new methods of managing this power. So not just simple power caps, but some very aggressive steps and technologies to make this far more efficient, and we'll be talking about that. Okay, so the foundation, we've already mentioned this. See, I think this is the right guy. Okay, so over here, so Moab, if you guys are familiar with Moab, Moab is quite interesting in that it can connect to any number of data sources. It obviously can connect to something like Torque, learn about your nodes, learn about your inventory, learn about your configuration. It can also talk to power management services. So it can talk to your it can talk to your chillers, it can talk to your backup power supplies, it can talk to your hardware monitors. So in this case, we've actually connected it to the hardware monitors so we can import information about temperature, about power consumption, about node controls and other types of things. And so Moab will actually go ahead and import information about the workload and configuration through one resource manager and export decisions on how it dynamically controls and impacts the cluster to another. So using that information, we're able to correlate low-level consumption information with high-level job objects, and then we can actually start recording that so that you can know that this particular job will max out at 15 kilowatts of power, and over the life cycle, it'll actually consume so many kilojoules of energy. So we can actually track that, and then with templates, we have the ability to say jobs from this user, jobs using this data set, jobs using this application, will go ahead and have this type of power profile. Once we have the association between power and the jobs, we can begin intelligently and proactively scheduling. This is where the soft caps come in. The soft caps allow Moab to actually model these hard power caps that we knew about. So if we know that during certain hours we can only use up to 5 megawatts, the scheduler will search through its entire queue of workload and say, I found a job that will actually fit without running into this power cap, and I can intelligently reorder my workload to guarantee that each one of these things will run. And so just as right now when you're running a cluster, it's obvious that you know how many cores you have, it's obvious you know what your bandwidth is, you know what your memory is. These are fully managed, dedicated, allocated resources. So with these capabilities, we lay the foundation and we make power the same type of thing. It is a fully managed, fully controlled, fully scheduled resource right along with everything else. Well, using this foundation, there's something that's very important that comes along with it. One is accountability. Right now, there is not a user out there that knows, they have no idea how much power they're consuming, and if they have no idea, they have no motivation to change their behavior. They have no motivation to see if they could actually run their things with slightly different configurations, run it larger, run it smaller, run it at a lower P state. All of those things, they don't know, and they have no way to control it, so they're just using whatever's easy, whatever's convenient in a completely non-power aware manner. So you can have both individual job power budgets as well as now enabling organizational power budgets, so that there's now the motivation for people to begin to change their behaviors and optimize their workloads for power savings. Dynamic power caps are also now possible. We can actually handle the situation where we understand that during business hours you may have one power cap, during nighttime hours you may have another, on weekends you may have yet another. So you can actually have these dynamically changing scheduled power budgets, and you are intelligently scheduling, delaying certain jobs to run later at a better time. Another thing that's quite interesting is you can also enable power costing. You can figure out the cost of running a given job during peak hours where it may be expensive, or during off-time hours where it's less expensive, and users may choose to run their workload at a less expensive time and save on the budget that they will have. And it all comes down, the fundamental thing is predictive power management. I know what my budget is, I know what I'm consuming with each individual job, I'm now intelligently scheduling inside of that power budget. Okay, so the next step is active power enforcement. So what we've talked about so far is monitoring these workloads and understanding what their consumption is, and then just intelligently scheduling them in time and in space to handle it. But now what if we can actually use these facilities that HP and others have integrated into their systems? what if we could actually go ahead and intelligently suspend or hibernate or even power down compute nodes? Moab is really interesting. It doesn't just schedule now, it predicts out into the future. It knows what it's doing now, it knows what it's doing in 10 minutes, it knows what it's doing in an hour. Because of that, it knows which nodes it's not going to use. And if it knows it's not going to use them, it can go ahead and power some of these down, save you guys money. And we talked about this power budget, right? We said we've got this budget that changes over time. Well, the user's going to specify how much power he thinks he's going to use, but he's probably going to be a little bit conservative because he doesn't know exactly, because it can actually change, because he doesn't want his job to be terminated or canceled or something else. So you're probably, if you're scheduling to what the stated power budget is of each job, you'll probably have some spare capacity. With this predictive capability, Moab can begin to over-allocate or over-commit intelligently and say, you know what, I'm only using 85% of my budget, I can squeeze a few more in there, and if I run into trouble, I can make certain types of adjustments to fix the thing up and still stay inside my power cap. So another thing that's capable with this active power enforcement is user-specified P-state. If I'm now a user, I know I'm getting charged for all the power that I'm using, I can run my job a couple times and see where it runs the best, under what clock speed, what type of configuration, what type of size, and then once I figure that out, I can now submit my workload and say, I want to run my job with this particular P-state. I know I'm memory bound, I know that I'm CPU, I'm storage bound or IO bound. I know I'm not CPU bound, thus I know that I can actually reduce my clock rate, get done just as quickly, but save power and thus save money. So you can now allow jobs to be submitted in that way. Now we talked about these templates, which means if the user can specify what the ideal one is, so can Moab. Moab can actually figure out what is the ideal power state for a given application, and it can now begin launching these jobs with the associated P-state that makes the most sense. So this whole thing of Moab now being able to automatically do something and make the most sense all comes down to this concept of application modeling. It's great that we can model power. It's great that we can say, if I stick you in this P-state, you'll use this much power, and this other one. But in order for Moab to make a smart decision, it has to understand not only can the application survive different P-states, but what is the change in power consumption with those P-states, and more importantly, what is the impact on application performance? If I lower the P-state such that I'm using 10% less power, but I actually make it run 3 times as long, I'm not really doing anybody any good, right? The users will be mad, the site will be mad because they're actually spending more power, they're getting lower, more energy, they're getting lower throughput. So you have to begin doing application modeling, and so some of the enhancements we're doing in conjunction with NREL will enable this application modeling so we can understand, if I do this to the application, what will happen and what will happen, and then as Moab is trying to make its decisions to schedule out into the future, it will say, well, I'll take this job, I'll twist it this way, this job twisted this way, everything will fit and everything will be very close to its ideal and optimal efficiency. So I think that pretty much covers, but this right here, this is what's critical to allow the scheduler to be intelligent. So the scheduler can act right now, it can predict certain things, but this is the thing that allows it to optimize and truly be intelligent in the way it's managing stuff. So this is just kind of some benchmarks. People are doing these studies, these application models are occurring right now. This is a big area of research and effort right now in supercomputing. So there's multiple organizations, universities, government agencies, and even corporations that are trying to begin to figure out what these profiles are and what you can get away with, what you can pull off, and this is critical and fundamental to the success of this whole effort. But when you start bringing it all together, these dynamic power caps, you can get far better utilization than you can with a static power cap, significantly better. And then this right here, what we're seeing with NREL and what we'll probably see at other organizations is it isn't just going to be this long-term schedule. I want to schedule this budget here, this budget, and I'm going to plan this out for weeks in advance. You're also going to have other types of unexpected situations. The power company will call you up and do this on-demand power thing where they say, you know what, I need to yank another megawatt of power from you guys because I have a surge over here, or it's getting too hot out there, air conditioning is going up, I need you to increase or reduce your power. And so you have to do dynamic modifications to your power budget that you may only get an hour of notice or 2 hours of notice. So the scheduler has to be aware of these dynamically changing power budgets and power caps. So both this is the long-term and short-term. And so another interesting thing that's happening is NREL is they are taking all their heat. They've actually built their entire campus around this understanding that heat is not a waste product. Heat is actually a resource. And so it's kind of funny that they're actually asking Moab to go in and say, you know what, it's getting kind of cold out here in this particular building, or the water temperatures drop too low in the boiler that we need for the showers. We need you to put more jobs on the fire to warm it up so that we can heat our campus. And I never, I started in this space 20 years ago, and never would I have believed that we're using supercomputers to generate waste heat to heat a building. But it's pretty interesting and pretty fun. Another thing that's really coming that I think is interesting, everyone's familiar with preemption. Preemption means I've got a running job, I'm going to terminate that job somehow. I'm going to go ahead and suspend it, I'm going to go ahead and checkpoint it, I'm going to go ahead and requeue it, or I may just blow it away and get rid of it. But anything, whatever I'm doing, I'm trying to free up a CPU, I'm trying to free up memory, I'm trying to free up something so that other jobs can use it, or because I'm violating a policy. Well, power management gives you something really interesting. You can do P-state preemption. I've got a power cap, and I'm about to exceed it, and there's a big penalty if I do. Which job should I cancel? Well, guess what? You don't have to cancel any job. You can actually say, I'm going to apply a P-state. I'm going to leave all my jobs that are running, I don't need to checkpoint them, but I'm just going to squeeze them down a little bit into a slightly tighter box. And then suddenly, I can be as aggressive as I want to be on my soft power budgets, because I know that if I do have to back off, it doesn't hurt very bad. It doesn't actually cancel any job, I don't lose any workload, I just have one of my applications or a couple of my applications slow down. With that same thing, we use preemption also to help priority workload hop into the queue. It hops into the queue, it wants to run right away. We can do the same type of concept with this P-state preemption to actually allow this high priority workload to sneak into the system, go ahead and run right away, and get the type of latency and response time that it really needs. So this is really quite cool. And then the other thing that's interesting is P-state optimization. The optimal configuration for a given application at the application launch time may not match the ideal P-state later on. You may say the ideal thing is to actually squeeze it down a little bit when I start, but later on, 10 minutes later, an application completes. Power can be moved around from one application to another, so you may want to continuously go and reevaluate your applications and say, you know what, I'm actually going to add more power to you because you're now in a very compute intensive phase, or because some other workload's gone away and I have a little more space between my current usage and what my power cap is. So that's, the power management, it is actually quite cool. It is saving a lot of money. At the same time, it's enabling new capabilities. Some of these intelligent power management capabilities allow us to be very, very aggressive in that power, so you're using it. And the fact that we can enable accountability will allow users to be far more intelligent about how they actually design their applications to save everyone money, including themselves. So that's all I've got, unless there's any questions. Hey, Ian, you want to come up here? So, any questions out there? So that they can do that. The first time an application is run, Moab can actually track it and identify the amount of power and then associate it with the given job. So it can say, I've run you. Now if there's a situation where, I've got 5 different P-states I want to evaluate, 100% clock rate, 75% clock rate, with half my cores turned off, a couple of possibilities like that, that's something where we either administrators or the end users would want to go through and figure out those profiles and then come in and register and say, hey, these are my data points. Now, scheduler, you use those data points to figure out what the ideal combination is to run me in the way that's most cost effective and giving you the highest SLA. So.
But the application has to be run multiple times.
Yes. At this point, there's not a way to guess exactly how that application will respond. And there's research going on with that, but that's going to be a couple years before we can actually get there. So. Thank you, excellent question.
And one more point, the same application also with different input data set will have a different...
Correct. With data sets, different data sets that will respond differently, as well as if you have a heterogeneous environment, if you're running on different types of resources, with GPUs, without larger core counts, larger memory count, whatever, older generation of a motherboard, whatever, each of those things will be different, and so with these power profiles, you do have to be aware of each of the, you have to be aware of data set, application, and those types of things. Now, you don't have to get it exactly right. If you are roughly close, that you realize that this is a better idea, it's a step in the right direction to go from this P-state to this other one, it's probably worth it. So we don't need to stop and say, hey, if we can't get it perfect, let's not do it at all. Getting something that's a step in the right direction will save a lot of power. So, thank you. Any other questions? All right.